so we have two more topics left in Chapter 8. One of those topics is static equilibrium. So we've dealt with static equilibrium in some cases in Chapter 4. Right? If the net force on an object is 0, we said that the object wasn't accelerating, right? So the object would have a constant velocity. That's actually technically referred to as total mechanical equilibrium, right? So no net force. Static equilibrium is where there's no net force and the object's velocity is also 0, right? Static meaning stationary, equilibrium meaning the forces are balanced out. Right, so we've used properties of static equilibrium, like if you remember the bag of cement from the exam, or the traffic light problem. We were setting all the forces in both directions equal to 0. That was static equilibrium. But we have one more condition now, that we're looking at solid objects that can rotate. An object in static equilibrium also has to not be rotating. Right, so it can't have a linear velocity, it can't have a velocity in the XYZ direction, but it also can't be rotating, so it can't have an angular velocity. So the definition of static equilibrium for a solid body is that there's no net force acting on the object and there's no net torque. It's also stationary. Okay. So you can see by this definition that a lot of our techniques are going to be repeats of what we did in Chapter 4. Right? So we're going to use Newton's second law for linear motion, but we're also going to use Newton's second law for rotational motion to solve these types of problems. So again, no net force, no net torque, and the object is totally stationary. Right? No velocity, no angular velocity. So here's our strategy. Again, you'll see a lot of these steps are very similar to our problem-solving strategy for Chapter 4, but we've got to add a couple new steps because we're dealing with rotational dynamics now. So we start off drawing a free body diagram. Make sure we label all the forces acting on the object. Now that we're dealing with a shape, we want to draw our force vectors where they are being applied. Right? So basically, we're going to draw a picture of the object, kind of do a rough sketch, and then draw our force vectors where they're being applied, right? Because we're dealing with a steel beam or a sphere or a disc or something like that. Next, we're going to choose a convenient location for the axis of rotation, and I'll talk about where is typically the most convenient for each type of problem. We kind of dealt with that before for our first torque problem, our steel beam problem. So we want to pick an axis of rotation, preferably where there's a force being applied, because a lot of times we'll have a force that, let's say we're not being asked to find it, or we don't know the value of it, right? And if we want to eliminate that variable from our equation completely, we'll pick where that force is being applied to be the axis of rotation. And again, I'll show you that in a couple examples how that works. So once you pick your axis of rotation, you have to identify all the forces that are going to cause a torque on that object. That means any force that's being applied some distance from the axis of rotation and has a component that's perpendicular to the radius vector, right? So if we do the cross product and we get some value for the torque, we have to identify all those forces that are going to cause the object to rotate. So for each force that causes a torque, we want to make sure we can find the distance between the axis of rotation and where that force is being applied, because we're going to have to at least make an expression for those torques and possibly solve them in the problem. So we're going to set all the forces in the x and the y direction equal to 0, right, like we did in Chapter 4. Sometimes that might not be necessary, but it's still good practice to write Newton's second law in the x and the y direction, just in case there's a variable in that Newton's second law equation that comes up that we might need to solve for. Do the same thing for Newton's second law for rotational motion. So you set all the net torques on the object equal to 0. Right? So we're going to have three equations basically. F net in the x set equal to 0, F net in the y set equal to 0, and torque equal to 0. So we will, sometimes we'll switch it, right? This step right here, sometimes I like to switch it. I like to make clockwise positive and counterclockwise negative. As long as you're consistent throughout the whole problem, that's okay. Again, our convention is clockwise is negative, counterclockwise is positive. But again, we can switch, we can reverse those directions to make our problem more convenient. Okay. So basically, we're going to have three equations. Identify the variable, use our good algebra skills as we've been doing, and then identify the variable. Maybe you have to substitute some things. It's going to be a system of equations. So solve for whatever's missing, whether it's a force or a torque, or maybe it's a distance, right? Maybe it's a radius vector that you have to solve for, like how far is this force from the axis of rotation or something like that. Okay. So again, it's a lot of steps, but you'll notice that probably about 50% of this problem solving process we've done before in chapter 4. Writing Newton's second law in the x and y direction, setting it equal to 0 for a stationary object. So I've got a seesaw problem. This is usually a good introductory static equilibrium problem. So we want to balance a seesaw. So there are two people, John and Bob. We have their masses. John is 56 kilograms, Bob is 43 kilograms. So they want to balance on a seesaw. Now, if you're looking at one of the examples in the book, it's probably a fixed pivot point. Right, a seesaw, they put the pivot point in the center. Right, if you've ever been on a seesaw, the pivot point is in the center of the seesaw, and then two people, maybe the same masses, maybe different masses, are on either side. Right, and you seesaw, you use your legs to push yourself up and all that stuff. So a standard seesaw problem is the pivot point is fixed in the center, and what you'll do is say one person is less massive than the other, and you want to find out where those people have to be on the seesaw to balance it out. So this is a little bit different. John and Bob, these two people, they're going to be on the ends of the seesaw. So they're going to be on the very end of either side of the seesaw, and we have to move the pivot point to where the torque applied by John and the torque applied by Bob are equal in magnitude, opposite direction, so the seesaw does not rotate. So right now we're going to assume the mass of the seesaw is negligible. And I'm going to talk about the cases where the mass or the weight is not negligible. Right? So we'll talk about when we have to account for the mass of the actual object that's rotating. Because if the mass is not negligible, then the weight force is going to apply a torque. If you go back to our very first torque problem, we actually solved for the torque due to gravity. Okay, so in some cases we have to account for the mass of the object that's rotating. Alright, so John and Bob are on either side, right? So on the left side I put John, on the right side I put Bob. Okay, so they're on the ends, they're at fixed locations. We know the length of the seesaw is 1.75 meters. And our goal is to find where to put the fulcrum, right? Where to put the pivot point on the seesaw so that these two, the torques due to these two people, cancel each other out. So the way I drew this diagram, I've got the length of the seesaw marked, and then I've got the distance from John. Right? So the distance from the very left side to the pivot point, wherever that pivot point is going to be, is x. Right? So I introduced a variable x. You know, you can call it d or l or r, whatever, because it's a length, right? It's a distance. So we have to find that value. Right? We've got to find how far from John do we put this pivot point so that the seesaw is balanced? So the first thing I do, I draw a free body diagram like I used to. Okay, so here's my free body diagram. This is just for my Newton's second law in the y direction. All right. As you can see, we've got no forces in the x direction. Right, nobody's pushing or pulling on the seesaw. The forces that we have are the gravitational force due to John. Right, because this is a third law pair. Right, we've got the normal force due to the seesaw on John, the normal force due to John on the seesaw. But if we were to draw a free body diagram of just John, the normal force on John and John's gravitational force would be equal. So the force that John is applying on the seesaw is the weight force due to John's mass. Same thing with Bob. It's in the same direction. It's in the negative y direction. Okay. Now we do have a weight force, but the problem told us it was negligible. Okay, so we can ignore that for now. So I start out like I did in chapter 4, Newton's second law in the x direction equal to 0. Newton's second law in the y direction also equal to 0. What are our forces in the y direction? I've got the force due to the pivot point, okay, due to this fulcrum in the positive y. That's a contact force. And then I've got the two weight forces due to John and Bob in the negative y direction. Okay. Now this, I know the masses of John and Bob. I could solve for A. So go ahead for fun, solve for the force due to the fulcrum. It's not asking for that, but in other static equilibrium problems, that may be something we can ask for. So that's a nice equation here. One equation, one variable, we can solve for that if we need to. This is the additional step, right? This is the chapter 8 step. I draw a second diagram for the seesaw, and then I draw all the forces due to John, Bob, the fulcrum, but I draw them where they're being applied, right? So the weight force due to John is on this end, the weight force due to Bob is on this end, the applied force is a distance x from John, right? I don't know where that is yet. But what I notice is this distance is x, right? So the distance between where I'm going to apply the fulcrum and John is x. The distance between the end of the seesaw where Bob is and where we want to put that fulcrum is 1.75 meters minus x, right? So it's the length of the entire seesaw minus x. Okay, so I don't know how far Bob is yet because I don't know where I'm putting the fulcrum, but I have two expressions for the distances but from, or where John is from the fulcrum and where Bob is from the fulcrum. So we have to be able to write expressions because we need to write expressions for the torques due to John and Bob. So I'm picking this point where I'm going to put the pivot point at as the axis of rotation, because in this problem I could find the applied force. Okay, that's all right. I could find the applied force in this problem and you know, include this in my Newton's second law for rotational motion. But in a lot of cases we won't have enough information to find a certain force, right? So what I'm doing is I'm just eliminating this force, right? They're not asking us for it, so I'm eliminating the torque due to this force by putting my axis of rotation right there. And that's what I was talking about when I meant, or when I said picking a convenient axis of rotation, okay? Because I know John's weight force, I know Bob's weight force. I've got to pick a position that position for the pivot point to balance the seesaw out. So F applied isn't relevant, and I don't need to solve for it, so it's good to just eliminate that variable from my third Newton's second law statement. So here's my third Newton's second law equation for rotational motion. The torques due to Bob and due to John. So in this case, again, these can be reversed. The signs of these can be reversed. If you pick clockwise to be negative, counterclockwise to be positive, we're still going to get the same. We're still going to get the same solution. All right, because I'm going to add this to both sides, and so this torque is going to be equal to this torque. So that makes sense, right? Static equilibrium. I want this torque and this torque to balance each other out, right? So I want this torque to be equal to this torque. So we use our cross product definition for torque, RF sine theta, for both John and Bob. Now, if you notice, our R vectors go like this. Right? There's John's R vector, goes like that. Bob's R vector goes like this. So John and Bob are both applying forces that are perpendicular to their respective radius vectors, or their lever arms. Okay? So the angle between these two vectors in both of these cases is 90. So sine of 90 is 1. Again, we're getting kind of lucky here. These trig values are going away because these two vectors are perpendicular to each other. Net torque, I'm setting equal to 0. Static equilibrium problem, I want the seesaw balanced and stationary. So now I'm going to substitute my expressions in for the forces due to John and Bob. They're their weight forces. Okay, MVG, MJG, I'm going to substitute those in for Bob's force and John's force. Now the radius vectors, my expressions, are this. John's radius vector is x, Bob's radius vector is 1.75 meters minus x. Alright, so that's why making an expression for Bob's radius vector is so important here. So we have to substitute these expressions in for r sub b and r sub j. So now I'm ready, right? So I substitute all these things in, my radius vector expressions, my weight forces, I substitute them in. Let's get rid of that g. I've got g over here, 0 over here. I can divide everything by g, get rid of g. And at the same time, I'm going to add this term to both sides. Okay, John's radius vector times John's weight force. So I have m sub j times x is m sub b times the quantity 1.75 minus x. What am I solving for? I'm solving for this x, right? Because I want to know the distance between John on the end of the seesaw and where I have to put the pivot point. So I've got a nice one equation, one variable, ready to solve it. Takes a little bit of algebra. I've got x on both sides. This x is trapped here inside the parentheses, so I gotta get this x out of here. So distribute this m sub b to both of these terms. I have 1.75 m sub b minus x times m sub b. Get both of these terms on one side of the equation. Add m sub b times x to both sides. So I've got my terms with x on one side, and I've got another term, everything that's left on the other side, right? I know the masses, okay, but I don't want to plug them in just yet. Finish doing my algebra, get a nice expression for x. I'm dropping units here. If you notice 1.75 meters, I'm dropping it, right? Just for the sake of simplicity, so I don't get too cluttered up here in my algebra steps here. I don't want to confuse that with a mass, so factor out the x. I've got the quantity m sub j plus m sub b. Divide both sides by m sub j plus m sub b. I've got a nice expression for x, which is what I'm solving for. Now I'm ready to substitute my masses in. 43 kilograms for Bob, 56 kilograms for John, and I'm ready to calculate. Okay, and I get 0.76 meters from John. Now, is this a practical answer? Let's go back to our problem. We know John is more massive. We know John is more massive than Bob. Okay, so torque for a torque that's being applied perpendicular to its lever arm is just R times F. So it's a product of R and F. So John's force is larger, which means he has to be closer to the fulcrum to apply the same torque as Bob, who is less massive. Bob is less massive. Bob has to be farther away so that Bob generates a greater torque than John. Okay, so this makes sense, right? The fulcrum has to be a little closer to John so that their torques due to their gravitational forces balance each other out. All right, and so this, again, a problem that you'll see in a book, or I think a WebAssign problem does this. You move the two people, right? There are two people on either side of the seesaw, and the pivot point is in the center. So you know there are vectors, or you know one R vector, and they say move somebody in closer so that their torques balance each other out. Okay, it's a nicer problem. It's a little simpler problem than this, but the principle is basically the same, except you're moving a person, except for the pivot point. Okay, so we've got a good biomechanics problem here. All right, I don't know if there are any. I think we've got some PT people in here, kinesiology people. So this is pretty useful. This will help you in your biomechanics course. So we've got a person holding a bowling ball, and their forearm is parallel to the floor. Right? So their forearm is parallel to the floor. So they're like in the middle of like a curling motion. Right? So their arm is parallel to the floor. The biceps muscle is applying a force to the forearm. The bowling ball is applying a weight force to the forearm. And also, this isn't anatomically correct necessarily, because the humerus will actually apply a contact force kind of at an angle. All right, but for the sake of simplicity, we're going to say that the humerus force is going to apply a contact force straight down in the negative y direction. Again, the way this joint is shaped is that it's kind of in this direction, right? But what we'll do is we'll simplify it. We'll say it's acting in the negative y direction. So the person's holding the bowling ball. We want to know the force due to the biceps to keep the forearm stationary, and then we want to know what the force due to the humerus is to keep the forearm stationary. So we've got three forces, 1, 2, 3, the humerus force, biceps force, and the bowling ball force. We're assuming the forearm is massless. I'll talk about how this changes if we account for the mass of the forearm, just in case there's a WebAssign problem where we have to account for the center of mass for the forearm, for the actual object that we don't want to rotate. So we're going to set it up the same way as a seesaw. Free body diagram. I'm going to model the forearm as a beam, right, or a long solid rod. I've got the humerus force in the negative y direction. I've got the weight force due to the bowling ball in the negative y direction. And here's one of those cases again where they just give us the weight. Right? I don't have to multiply this number by g or anything like that. It's not a mass. They're giving it to us in newtons. So the weight force due to the bowling ball is in newtons. So I don't have to multiply that by g or anything like that. Okay. If we could not neglect the mass of the forearm, we would have to take the length of the forearm, divide it by 2, and then I would have a weight force due to the forearm right in the center. So I would have another vector in the y direction right here in the center. Okay. So if this were the case, I'd be given the mass of the forearm, and I'd be given the distance, right? The length of the forearm is 0.35 meters. I would divide that by 2. That would be the location where the gravitational force on the forearm is acting. So I would just have another force in the negative y direction, and I'd have to include that force in my Newton's second law problems. So F net in the x direction is 0. All of our forces are acting in the y direction. That's great. F net in the y direction, I've got the biceps force acting in the positive y. I've got the humerus force and the bowling ball's weight force in the negative y direction. Again, it's a static equilibrium problem. Set them equal to 0. So now we run into a problem, right? We got this, the last problem, it only had one variable in it. We could have solved for it. And now we've got an issue. These are the two forces that we're looking for, and they're both in the same equation. So I can't stop here because these two equations by themselves won't get me the value of the biceps force and the humerus force. So I have to sum up all the torques acting on the forearm. So now in this case, there are a couple different options that we can determine where the pivot point is. Some diagrams, they just kind of lend us a nice hint as to what a convenient pivot point is. I could pick right here where the biceps force is, right? Because I know the distance between here and where the humerus force is being applied, and I know the distance between where the biceps force is being applied and then the bowling ball, right? So I could pick this point. I could even pick right here, right? I could pick the bowling ball, the location of the bowling ball, because I know the distances between these three different pivot points. I can find the distances between the pivot point and the other forces. But I'm going to pick this, right? I'm going to pick the end of the forearm. I'm going to pick where the humerus force is being applied. I think that's going to be the most convenient. And the reason I'm doing that is because my net torque equation is not going to include the humerus force. Why not? If I pick this pivot point, the humerus force is acting on that pivot point. The radius vector, right, if I were to try to calculate the torque on this humerus force, the radius vector would be 0. So this is actually not applying a torque based on my coordinate system, based on where I choose the pivot point. So that eliminates any torque due to the humerus force in my third Newton's second law equation. So all I have to do is write expressions for the two torques due to the biceps force and then the weight force of the bowling ball. And I'm doing that because I don't want a second variable. I could solve it, right? If I picked a different axis, I could solve it. But I want to eliminate this variable f sub h out of this equation, right? It'll just make my algebra nicer, right? Rather than having two equations and two variables, I can solve this tau net equation for the biceps force, and then I can come up here and substitute it in and then solve for the humerus force. That's my preferred method. I like to eliminate variables whenever possible. So I'm picking the end of the forearm, basically the elbow joint, as my pivot point. So now I have two torques. I've got the torque due to the biceps force and then the torque due to the bowling ball's weight force. Now I'm switching it around, right? I'm going back to counterclockwise is positive, clockwise is negative, right? If there was just the biceps force, the forearm would curl up towards the shoulder, right? If there was just the bowling ball force, the forearm would rotate clockwise down towards the floor, okay? So I'm switching my coordinate system. Again, it doesn't matter if you pick this to be positive and this to be negative, it would be okay. We'd still get the same expression for the biceps force. So my torque, my cross products, my cross product expressions for the torques look like this: biceps force times the biceps radius vector. Again, we've got this nice situation where all of the forces are perpendicular to their respective radius arms. So the sine thetas go away for both of these because sine of 90 is 1. What are the values for our radius vectors? So we need r sub b for the bicep muscle and r sub bb for the bowling ball. So I'll go back to this diagram. The biceps force is being applied 0.03 meters. Right? See this right here? See these two arrows? This is kind of like a mechanical drawing or a drafting notation here. These two arrows are telling me that this width right here is 0.03 meters. All right. So that's the radius vector for the biceps. The 0.35 meters, this label right here, is the distance between my pivot point and where the bowling ball is applying a force. So I've got my R vectors. It's very nice. I've got numbers. A lot nicer than that seesaw problem where I had to make expressions. So I've got numbers for these, and I also have M sub BBG, right? That's the weight of the bowling ball. So that's 50 newtons. That is 0.03 meters. That's 0.35 meters. I'm ready to do my algebra and solve for the biceps force. So I'm going to get rid of my sine theta terms because they're equal to 1. Add mgr of the bowling ball to both sides. And so now I have the torque due to the biceps force is equal to the torque due to the bowling ball. Again, if you picked clockwise to be positive and counterclockwise to be negative, you'd still get this equation right here. You'd still get the same thing. So now we're ready to solve for the biceps force. All I have to do is divide both sides by the biceps radius vector. I've got a nice expression here. 50 newtons is the weight force, mg, of the bowling ball. 0.35 meters is the bowling ball's radius vector. 0.03 meters is the biceps radius vector. Plug all that in. I've got a very strong force, right? A very high value for the biceps force, 583.3 newtons. Okay. If you ever held a bowling ball, they're like anywhere from like 12 to 18 ounces or something like that. So they're pretty heavy. So now that we have the biceps force, we're going to go back to this. Again, all that stuff we did in chapter 4 is important because I have to have this equation to solve for the humerus force. I used this to solve for the biceps force. So now I'm going to take my Newton's second law equation in the y direction, and I'm going to solve this for the humerus force. So I can add the humerus force to both sides. The humerus force is equal to the biceps force minus the gravitational force on the bowling ball. I've got the gravitational force again. I found the biceps force. Just plug it in, calculate it, and the humerus force is 533 newtons. So that means the biceps force, this should work out, the biceps force is equal to the sum of the humerus force and the weight force on the bowling ball, right? And which agrees with this equation right here, and agrees with the fact that the forearm is stationary, right? All the forces in the y direction are canceling each other out, and all the torques in the y direction are canceling each other out. Okay, so I'm going to start angular momentum in the next video, and that should be the last of our chapter 8 content. Okay, thanks.